Okay, so one-way slab can be either according to the Ly over Lx, or it's depend on the way it support the slab supported by the brick wall or beam. Yeah? For example, here you can see that the slab is supported by wall or beam only two side, two side here, two side, you know, opposite, yeah? Not adjacent but the opposite. Okay, Jialin want to join in. Okay, so in this type of slab, so it is one-way slab, and the span is between the beam. Yeah, it's supported by beam. Okay, so the L that you considered for design is the LEF here, between these two beams. Okay, so we take 1 meter width. Okay, 1 meter width of the slab. You know, the slab here we got B, yeah, but the B for the slab is just 1,000, and then we fix, or we determine the span, and then it is simply spotted. That's why we can use the formula WL square over 8 to get the maximum moment. Yeah. Meaning that we need to design for 1 meter width only. Although you can see here that the width is, we don't know the width here, yeah, but we take only 1 meter width and then design. Okay, and the steel, we have the main steel here. This is main steel, the black one, and the red one is the traverse steel or secondary steel. You can join in. Izham Nur Sharini. Okay, so we have only main steel at the L direction here, LEF. Sharini. Okay. Now this is another one-way slab. Yeah. Okay. Opposite of the beam now is placed at the long direction here. The longer side here. Yeah, so there's no beam here and there's no beam here. It's opposite here. So we got this beam and this beam become a support for the slab. Therefore, we need to design 1 meter width here. 1 meter width, and then we find the GK, QK, and then get the maximum moment at the mid span. So similar like previous one, except that this one is the shorter length here become the span of the slab. Okay, next one is here. If we have the slab supported by a beam, yeah, in the all edges, at all edges is supported by the beam, but we calculate Ly over Lx greater than 2. Yeah, so in this case you need only to design according to the shorter direction. Why shorter direction? Yeah. It is because of as last time I explained that crack will happen here. Crack happen here along the long direction. Therefore, in order to avoid the crack, we need to design opposite of this crack. Yeah? Meaning that we need to put the steel, main steel here, opposite of the crack to avoid the crack. Therefore, this is the direction of our design. The slab configuration will be in the shorter direction. We using the simplified formula L square over 8. Okay. Now, if we have a plan like this, yeah, 2 panel, in this case also, since it is surrounded by the beam, the slab, this is P1. You can see here, let's say this is P1. And this is P2. P2. So we have two panel. Yeah. What you can do is that determine what is P1 and P2. Is it one way or two way? Let's say here it both is one way. Therefore, you need to imagine the crack. A crack must be along the longer direction. CT. Join in. Okay, therefore, the configuration of the slab for P1 is 1 meter width, like that, and the second slab is 1 meter width, like this. So therefore, this is one-way slab, therefore we design only one of them, represented by these figures. So with the maximum moment WL square over 8. Okay. Any question? You can on your mic to ask me a question. Okay. Now, let's say now we have a slab like this. Student join in. Okay, if you have a slab like this, we have P1 here, P1, and then P2, here, P3, P4. So we have 4 panels. Before you proceed, you need to identify the panel. Here we got a beam, here beam. The dotted line shows that the beam underneath of the slab. And then you can see here this is free, because only one line here, so this is free edge. This is free edge. Again here, this side also free edge. Free edge. Therefore, this slab is only supported by the beam in y axis. So when you design, this is the pattern of cracking will be like this. This is also in this direction. Here also. Here also. So this is the pattern of cracking. Therefore, in order to eliminate the crack, what we need to do is that by putting the steel in this direction, and also this direction. Therefore, this is when we design. You must take this one as 1 meter width, 1 meter width this direction, 1 meter width here, and 1 meter width. Okay, now we have 1 meter from this support to this support, 1 meter from this support to the support, so on. And then you need to understand during the construction, we will cast the beam and slab together, yeah, or we call it as monolithic. Yeah, we call it as monolithic. In design, we call it as monolithic construction. So it's called monolithic construction. Monolithic construction. Sorry, it is a monolithic construction. So this is monolithic construction. Therefore, during design, we cannot assume it as simply spotted. Yeah, simply spotted here, simply spotted here, simply spotted here, and so on. So what we need to do is that design from here to here. Yeah, 1 meter width. Therefore, it is one-way continuous slab. So we have a configuration like this, yeah? As I shown here. You will have the continuous beam, yeah, over the supported by the beam. Yeah? Therefore, we got a moment like this, because this is continuous, yeah, continuous slab. If you assume that at the end of here, the end support is pin means we don't have moment is 0. So the moment is 0 here. We assume that this is pin at this point is pin. Yeah. So moment is equal to 0. So moment is 0. We got end span. We have a maximum here at the support, yeah, at the middle span. So we have the moment like analysis in the beam. Yeah. So what we need to find here is that what is the moment at the span and also at the support. Yeah. So when we got that, then we will do the design. So this is the steel arrangement. You need to understand the steel arrangement, since this is the maximum moment here. So we need a steel here, main steel. Yeah? So this is main steel moment here. So when you design, you got this steel, main steel, right? And then for the moment at the support, you will get this moment. Yeah? This one, the bold one. And this is called main steel. At the span here, okay, at the support, okay. Yeah, so easy. It's just like design for a beam, yeah? Except for the beam we don't have traverse steel here, the secondary steel. The secondary steel, the dot that you see here is the secondary steel. Yeah? That we the calculation is similar with the simply spotted just now. At the mid span we have the secondary steel. Okay, so the problem is that how to get the moment, yeah? The moment here. So how to get the moment here is the problem. So like in the beam, yeah, we need to erase first. Remember this table, it's similar with the analysis in the beam, but here we got two assumption, pin and continuous. we have outer support, near, middle, and span. Outer support continuous. Okay, someone to join in is satu as well. Okay, now we have okay, now we have table 3.12. Yeah, we have a simple method to get the moment and shear force. Yeah? It's just like analysis in the beam. We have the coefficient here. Okay, so now let's look the here. Okay, and show. Yeah? I need to get this. I need to crop it. Easy. Yeah. Okay. Now we have survey to reduce a bit. Okay. Okay. Adelan want to join. Sorry. Okay. Okay. Now, let's say now we have a continuous slab like this. Yeah, this is the provision of the steel that we imagine. Yeah. So now we need to find what is the moment and also shear from this table 3.15. Yeah, in your design formula. Okay. Before that, we need to identify what is the outer support. So this is outer support. Yeah, outer support. So this is outer support. OS, outer support. Yeah. Outer support. Near middle of end span. Yeah, near middle of end span here. Near middle end span, yeah, NMES. Then at first interior support, FIS. This is similar with the beam. Yeah? First interior support. Okay, you can start both sides. Yeah? OS again, NMES, FIS, and then middle interior span. Called middle interior span, middle interior span miss, yeah. Middle interior span, and then middle interior support. Okay, interior support. This is interior support IS. Okay, right. So it will we repeat again here. Okay. Now. Shear force. The first one is shear force. Outer support. Yeah? Outer support. Now look at this. Pin and continuous. So it's up to you. It's your assumption. If you assume that at outer support here is pin. Yeah? Do you know pin? Pin is without moment. It's only we have only vertical reaction. Yeah? Pin. So if you assume here pin, then we can choose here 0 moment and 0.4 F. Let's say we assume it's spin. Yeah? So here is spin. pin here. At OS, a pin at OS outer support. Now we have shear 0.45. 0.45. Therefore, 0.45, here is 0.45. 0.45F. 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 And then, okay, at first interior support, at first, at outer support, it is continuous. At first interior support, this is first interior support, it becomes 0.6F. Yeah, here 0.6F. 0.6F. Okay. Then 0.6F. And then interior support 0.5F. Here we call it as 0.5F. And we will repeat again 0.5 here, 0.5F, then 0.5, here 0.5. Again, here is 0.5. Sorry, here 0.6 and here 0.5. Okay, then we can draw the shear force. Yeah. So it's like that. Yeah. Then 0.5, 0.5, 0.6, 0.45. Okay. So that is the shear force when we assume it as a pin at outer support. And the moment here is that zero moment. Yeah. Here, zero moment. And then near middle of end span 0.0, 0.075 FL. So we have 0.086. 0.086. Here is 0.086 FL. Then the first interior spot 0.086. 0.086 FL. Okay, middle interior span 0.063. 0.063 FL. Yeah, at the interior support also 0.063. Yeah. 0.063 FL. And then you can repeat again. Yeah, start from the right. Here 0.086 FL. Here is again 0.086 FL. Then 0.063 FL. Yeah. Okay, that is the moment. Okay, for the slab, one-way slab. Yeah. And then what is F? F is remember the beam. Yeah. So F is equal W L. Yeah. While Okay, the F is WL. So L must be, we have and show, then let us see here formula. Okay. Table 3.14, right? Is design. This one is for the beam. Okay, let us erase first. Okay, the what is F mentioned here, 1.35 GK plus 1.5 QK. That means GK on the slab and QK on the slab, not on the beam. Yeah? Look at the now the small letter here, QK. Okay. Then for slab carrying uniformly distributed load and continues over 3 or more nearly equal span. Yeah. So the key important things here is it must be nearly equal span, continuous over 3, and also it must be carrying UDL. This is the condition, yeah, to use this table. Uniformly distributed load, continuous over 3 or more span, and the span nearly equal. So we can use this table. Yeah? What is nearly equal span? So the variation between the adjacent span is less than 15%. Basically, we use 15%. So if there's a point load, then you can use linear elastic method such as moment distribution or moment deflection. Okay. Any question? Ada soalan? Any question? Ada soalan
Ada.
Yeah. Okay. Okay, this one is for the second one, yeah. Okay. Alright. Okay. Now the second one is that if you assume it as continuous, yeah, meaning that we need to. The difference is that at this outer support, it is fixed. We got a moment here. Look at there, the moment. Yeah, we have the moment here as much as 0.46. The moment, the value of moment, 0.46 here. 0.46 FL. 0.04. Sorry, 0.04. 0.04 FL. Okay, if you can see the table. See from the table here, 0.04 FL. Put here. also the other, okay, for the near, middle and span, since we have a moment here, then the middle of end span moment will be reduced to 0.075 fl. 0.075 fl. 0.075 fl. Okay. Now at the support, is it still the same? At first interior support, yeah, this one maintain 0.086. The first interior support 0.086. 0.086 fl. Okay. Then you can repeat. Sorry. So here we got 0.063 fl and so on. So here is equal with this one 0.075 fl. Here is 0.08. 0.086 fl. Okay. Now, yeah. So you can see the difference, yeah, 0.0 f for fl. Okay, the shear force also different. Here we got 0.46 f, 0.46 instead of 0.4. So we have 0.46. At first, at the outer support here we have 0.46 f. Okay. Second one we have 0.6. 0.6. Second one here is 0.5. 5 f. Here is 0.5. And we need to repeat again. So then we can draw the shear force. So you can continue 0.5 and 0.6, 0.46. Here is 0.46. Right, so you can see the difference, yeah. But actually, since we have a moment, therefore we have the steel here. Yeah, we have the steel here. Okay, we have the steel. We need to design, so we have a steel here. Okay, again also we have the steel. Like that. So that is the difference between the simply we assume with no moment, so we don't have to design at this support. But if we assume it as continuous, so we need to design the steel over here. So this steel will provide the fixed condition of the slab. Okay. Okay. Any question? No question, yeah. So we go to the example. Yeah. So I need to erase. Yes. Okay, now we have an example of continuous one-way slab. Why one-way slab? Yeah. Look at the slab. Yeah? We have the dimension here. Okay, admit all. Okay. Satu, join in. Okay, look at the plan. Okay, now we have a panel P1, P2, P3, and 4 panels. 1, 2, 3, 4. So we have 4 panels surrounded by the beam. Yeah? So this is the beam. Now, this is one-way slab, given by the symbol, or you can divide Ly over Lx. So it's greater than 2. As I said just now, you can see that this is one-way slab, one-way slab. So every panel is one-way slab. So during construction, we will cast all of them together with the beam. So it is monolithic, restrained, monolithic. Therefore, we need to design it as one-way slab, one-way slab. Okay, meaning that we need to design from here to here. One-way slab. So it is continuous. And when we talk about continuous, we need to consider the negative moment at the support. Okay. Now look at the data. Before that, the most important thing for the design of slab is that you are able to identify, is it the direction of the slab, the direction of the slab configuration. So in this slab, we have continuous slab with L 4 meter, 4 meter, 4 meter, and then 4 meter. So don't be confused. You need to understand, okay, why this is one-way slab. Always remember the cracking pattern. Always remember the cracking pattern will be this way. The spiral to the longer side of the slab. Therefore, to avoid this crack pattern, you need stills. You need steel this direction to avoid the crack. Bottom and top and bottom. Yeah, that is the philosophy behind how to get the slab configuration. Because when you let's say you decide a wrong way, your slab direction 9 meter, you design as 9 meter, simply spotted 9 meter. Then if in a final exam or in a test, you will get 0 mark. That is very important. Okay. After you understand that, it takes some time. So when you answer in a final exam or in a test, think carefully about the configuration. Okay, now we have data given. Permanent GK 1.0. Permanent GK means load from the finishers. Just like the tile is the finishers, the shielding and so on. So usually we will take about 1 kilonewton, 1.0 kilonewton per meter square. This is exclude the self weight of the slab. So in the project also, you need the permanent GK that I gave to you is actually the permanent GK from the finishers. It's not include the self weight. The self weight you need to calculate the thickness times with the density of concrete. Okay. Permanent QK, permanent QK here given. Design life 50 years. This is a normal building, so it is 50 years. Fire resistant 60 minutes, 1 hour. Exposure classes XC1. Let's say this is XC1. So the concrete grade, if you see the table, the minimum is 20. So here we use 25. You can see here. Okay, here you rotate you clockwise. Okay, you can see here XC1, the minimum is C20. C20. So now we use 25. It's okay because this is the minimum strength versus 20. Okay. Okay. Steel is fixed. The value of steel is fixed 500. Unit of weight of concrete also fixed. Assume that bar is 10 millimeter. So in this question, in this example, the bar that we use must be 10 millimeter. If it's not stated, then you can use 6, 8, 10. Okay, now the thickness is not given, only the span given and the load and the action. Therefore, we need to find the thickness as in the case of last example. We need to find what is the slab thickness. Okay, now we have two guidance to obtain the slab thickness. The first one is the fire resistant. So look at here, the fire resistant. Rotate clockwise. Okay, what is fire resistant? This is for beam. This is beam reinforced. Okay, here we have a one-way and two-way slab. Okay, it's 60, it's 100, 100 here. So you have 100 here. Sorry, it is 100. 80 or 100? 80, if not mistaken. Is 60 is 80, the minimum thickness, 80 here. 80 here. Okay. So look at our example. So it is 80. Then we have another guidance, that is deflection control. L over H is equal 30. How to get 30? Why is 30? Look at the notes. Okay. Here, if you can see here, L over H is between 20 to 30. Between 20 to 30. So you can choose one number here between 20 to 30. So in this case, we choose 30. Let's say we choose 30. So we have 4,000 divided by 30. So you have 133. Therefore, H is 150. Choose the greater than 133. That is 150. Then the next step is to find the cover. It's because the cover is not given here. So the cover must be determined according to the 3 parameters. Last time Sometimes a student asks me why we need to consider the bond. Why? Because this is according to the Eurocode. Yeah, look at here. Cover. Why is it cover? Okay. Cover, concrete cover. Yeah. C norm is equal C mean plus deviation. Deviation must be taken as 10. So C mean is due to the 3 parameter. The first one is minimum cover for bond. Look at here. For the bond, it must be determined either your bar will be a position separated or bundled. So in the case of slab, we will arrange in a separated way. Therefore, it's equal, the C minimum is equal to the diameter of the bar. Therefore, here we got 10 millimeter, because 10 millimeter is the minimum. The given diameter here, 10 millimeter. Therefore, we put 10 meter. Because we will arrange like this. Look, this is separated. Okay, minimum cover due to durability, 15 millimeter. So how to get this? 15 millimeter. We need to see table 4.4. Okay, minimum cover for durability. Now, table 4.4. Okay. Now our structure S4. Before that, we need to go to this table 4.3. Refer to this 4.3. We assume assume for the normal building is S4. Okay. The assumption is S4. Yeah, default. To use this table, we must start with S4. Then we need to find what is the real S4 that we gonna use. So although our design is building S4, but we need to consider 4.3. Therefore, the real S, what is the real S? Is equal 4 that we assume 4 here. Okay, and then just now we classified as XC1. So design working life 100. Is it our design life is 100? No. So we need to omit this, increase by 2. The second one is our strength classes greater than 30? No. If there is, then we reduce by 1. Member with slab geometry? Yes. Reduce by 1. Minus 1. Yeah, because this is reduced by 1. Special quality control? No, we don't consider it. Therefore, we have 3. Therefore, our S now is become S3. Okay, then when we got S3, then go to the table. This table 4.4. Our one is now S3. Here S3. And the is S XC1. Yeah? So we got 10 millimeter. The cover now is 10 millimeter. Okay, look at here. Minimum cover is 15. Why 15? 10 millimeter. Yeah? Actually, it's 10 millimeter. Okay, because 4 minus 1. Just now we need to minus 1, right? Here, reduce by 1. Okay, member with slab geometry, reduce by 1. Therefore, it is 10 millimeter. Okay, 10 millimeter. So we have sorry, this is 10 millimeter. Yeah? Change to the 10. Okay. So we have. Okay. Now we have minimum cover for durability is 10. Okay. The third one, the last one that we must consider is the fire resistant. Okay, fire resistant. Okay, we need to find what is A. Yeah? Fire resistant. This is for the beam. This is for the also for the beam. Okay, this is for the slab. This just now is 60. Our resistance is 60, and one-way spanning slab 20. Yeah, this is the value of A. The A. Therefore, back to the here, A is 20. Yeah. Therefore, you can calculate C min 20 minus half of the diameter bar. So you got 15. Alright, so we have now cover due to fire is 15, due to bond 10, due to durability is 10. Yeah. Between these three, we take the highest value, then add with deviation 10. Therefore, you got 25 here. Okay, 10 so 25. The C. Okay, yeah, we have obtained the cover. So the next one is the what do you call action? Yeah? Slab weight. Is the thickness times with the density of concrete. So you got 3.75 permanent excluding weight, excluding self weight. So you need to total it up 4.75, and then we calculate N. Therefore we got N. Alright, continuous one-way slab. This is continuous one-way slab. Okay, now we have here the condition here, as you can see here. This is actually from the BS 8110. Yeah, this is the condition that we need to consider before we use the coefficient in table 3.12 just now. The area of the bay must be greater than 30 here. 30. It must be 30. This is the fixed. The number is fixed. 30. What is bay? Okay, you can see here. This is one panel. Yeah, this is one panel. From here to here, we call it as one panel. Yeah, this is one panel. Panel. Okay. This is one panel. So from here to here, yeah, we have 4 panels. 1, 2, 3, 4. The area of all the panels under the consideration here is called one bay. This is one bay. Satu bay, one bay. If we just got 3, so one bay is equal to the area of the 3 panel. So we have now 4 panel. 1 panel, 2, 3, 4. So 9 times 4 is 36. 36 times 4. So you have one bay is equal with the 144 here. Yeah. So therefore, one bay area is greater than 30 meter square. Yeah. Kumi want to join in. Okay. QK over GK is must be less than 1.25. Okay. This is also another requirement from the BS, and The last one is the 5.0 here. Your QK must be less than 5. Okay, so in addition to the nearly equal span. So if one of the condition is not fulfilled, then you cannot use table 3.5 just now. This is according to all the condition according to the S8110. Okay, now consider 1 meter slab. As you can remember just now, when we design, we must consider it as 1 meter width. Then with the slab configuration that we have determined before, so we have L is equal to 4. Every L here is 4 with W 11.7. So F is equal WL. F is equal WL. Therefore, now it's up to you. Yeah? Either you want to use outer support become a fixed end or pin. Yeah? So in this example, let us assume that it is fixed. Therefore, we have a moment over here 0.04. Here we have determined earlier on the value of the coefficient. Yeah. So this is the moment. Therefore, we need to design. We have 4 different moments at the outer support, at the near middle of end span, first interior support, and also middle span. Yeah, we have 4 different moments. Okay, your F, WL, so we have 46.7. Remember, L is not the cumulative L, but L for the single span. Yeah? This is the thing. This is the thing that you need to remember. Student always confuse the L. L must be for the single span, not the whole span. Remember that if you got different L, I would recommend you to choose the longest one. Yeah? Okay, D. Yeah? We now going to design the main reinforcement by calculating what is D. The D, remember, D is equal H C norm minus bar. So we have 120 here, and then calculate first the AS min and AS max with this formula. So you got here 156 6,000. Yeah? So although in the code the secondary bar will be based on 20% of the area of the steel at near middle of end span, but designers tend to use the minimum steel as a guidance to obtain the secondary bar. Therefore, we have here H10 4 to 5. How to get this one? Yeah, in our table here we haven't got that one. Let's see the table here. Okay, you can see here the size 10. Yeah, the minimum that we got here is 262. Yeah, so you may choose 300. Yeah, if you want to use the table. The solution here we calculate. Yeah, so you can change it to 300. 300, easy. I think is easy. Okay, 262 according to the table. Since this example requires you to to use H10. Okay, so this is secondary bar. What is secondary bar here? Is the secondary bar here. Here, secondary bar. Yeah, yeah. That is secondary bar. The dot one here is the secondary bar. That is secondary bar. If I can make it larger. So this is secondary bar actually, the dot one, secondary bar. Secondary bar is equal AS min. So every secondary bar here, dot, the dot you can see dot here is all secondary bar with the minimum AS min. Okay, so you don't need to design. Okay, back to our design here. This is the secondary bar H300. Okay, now we start with our design. Okay, so we must remember that we have 4 moments. So every moment that we have designed, we will produce a steel and the steel area, and the steel area must be within this range, AS min and ES max. Therefore, the first one we go is the first interior support. We have 16. Yeah, remember the B is 1000. Yeah, the method is similar with the beam, yeah, except here B is 1000, and area that you have here must be, the unit must be per meter, yeah, because we design as 1 meter width. So you got H10 225, 349, you base here, 324 is greater than AS min and AS max. Therefore, when you look table here, yeah, it must be based on this value 324, 324, 324, therefore 349 with the spacing 225. Therefore H10 225. Near and middle span, okay, and MES, we have this value, so we have 282 similar like above, so we have H10 275 is slightly greater from the table here to 314, yeah, 250, 250, yeah. We don't have 275 here. You can change 250, 250. Okay. Then at interior support, so you have you got 237. Yeah. Okay. Now we have 372. So 300. Look at the table here. So 300 262. And outer support here, look at here, this value is actually less than the minimum. The minimum here is 156. We have, therefore, we must choose the AS minimum. Since it is less than AS min, therefore we use AS min. Okay. Therefore, AS min, our AS min now is 156. 156 Therefore, look at here 156. There are any 156 here in the table. So the minimum one we got here is 262, 300. Yeah. So we need to put here 300. Okay. Alright. Now we have complete the design for the flexural reinforcement. Continuous, okay, shear. Shear, remember last time I mentioned that for this slab, the shear is usually minimum. Yeah. Therefore, we only do checking. We don't need to design. Therefore, choose the maximum one, that is 0.6. Just now we calculate, yeah, from the table we obtained that the maximum is 0.6. So don't bother the other value, just take the value of 0.6. Then we check the shear stress. Yeah? Maximum stress, shear stress in the concrete. So this is the formula. Yeah? Determine the K, determine the rho 1. This is the value of the maximum moment. Maximum moment at the span. Let's see here, maximum moment at the span, near middle of the span, and MES, anterior span is only 0.6. So we have 282. Yeah, 282. So you got here is 250. Interior support. So we have 250. Sorry, here is 250. Near middle of end span. So here is 250. Okay. Now we have a new here, the RDC, the capacity of shear force 49.9, and the minimum in the concrete is 5. You calculate from here the minimum 59.4. Okay, this is due to concrete alone. Yeah? This is given due to steel. So the VED is less than, we got 28 is less than both of them, yeah, 49 and also 59. Therefore, the slab will be safe from the excessive shear, so we don't need shear reinforcement. Deflection, okay, deflection will be considered for the moment maximum. Okay, where is the moment maximum here? Happen at the span. Look at here at the span, near middle of end span, we have moment is 14. Interior is only 11.8. Therefore, we consider this AS 282. 282. Okay, now calculate 282. Yeah. And then calculate the rho, and the factor for structural system K is 1.3. Okay, 1.3 because continuous slab. Therefore, we need to calculate LD allowable. This is what just now. 59.9 times 1. 1 because of less than 7 meter times the modification factor for the steel here. So you got 60.67. Actual span, yeah, is 3.3. Therefore, our checking shows that our slab is safe from the excessive deflection, since the actual L over D is much less than the allowable. Okay, continuous one-way slab for cracking. Yeah? The cracking, remember, our design must be less than 200. if we want to check using the simple method here. And our H is 150, therefore maximum slab, this is for the main steel, must be the spacing must be less than 3H or 400, which is lesser. So 3H 150 is 450, then we must take 400 as the max here. Okay, so bar maximum, our bar maximum, look at our bar main steel. The main steel, the maximum spacing is at interior support we have 300, outer support also we have 300, middle span 250 and 225. Therefore, the maximum for the main steel is 300. Therefore, now we have 300, 300, and it is less than 400. And for the secondary steel is 3.5H or 450. Therefore, we take the less value here, 450, and our secondary bar spacing is 300, so it is less than 450 here. Therefore, our slab is safe from the excessive cracking. Okay, now the detailed drawing. Okay, the plan, I would like to suggest you to do the cross section first. This is our cross section. The cross section is symmetry. It is enough if we show only two span. Only the first two span. Okay, you need to do the cross section first. If you can see here, the main steel at the near middle of end span, we name it as 01. At the support, at first interior support, we name it as 02. At middle span, 03. And at the middle support here, 04. And at outer support, 05. So here, based on this arrangement. Okay, now you need to locate the main steel first, 01. Okay, draw. You must put at outer layer. You can see here at outer layer. Outer layer. So this is the main steel. Okay, that is the main steel, 01. 01 is near middle of end span, and then this is 02. This is the main steel. Draw first the main steel like that. Here. And also at this span. Okay. So complete first. You need to complete the design, the drawing for the main steel. Then locate the secondary steel here. The dot one is the secondary. We name it secondary as 0.06. Kita namakan aja 06. So this is secondary steel. Just do dot. that. Okay, and so on here. So we have dot, this is secondary still. Yeah. So you got a lot of dot here showing that it is secondary still. Then after you complete the cross section, okay, after you complete the cross section, okay, let's say you have completed the cross section. I need to erase. Then you project the steel here to the plane, yeah, to the plane here. Okay, you draw the plane here, and then for example 0, 1, here 0, 1, 0, 1 is the near middle of end span. It must start here, yeah, one cover from the beam here. One cover here, this is one cover, to here, one cover from the beam, and just draw the arrow here, the arrow, and then draw one steel only to represent many of the steel here. Actually we have a lot of steel from here to here, and in the drawing we just show one of them, yeah, just show one of them only, yeah? And then put dot here, from here to here. This is 0, 1 located at the bottom. In the plan you cannot see either it is bottom or top, but you can see it by looking the number here, and also by referring at the cross section. Okay, the 07 is the 07 here. You can see 07 here. 07 is the secondary steel that accompanied the 01, yeah, and it must be located from here, one cover to the here. Okay, meaning that we have a lot of secondary steel, yeah, on top of the main steel just now. So again we need to show one of them only here. Okay, and then put the dot here. And do the similar way for the other steel, yeah. For example, here at the support we have 02, 02 must be located from here, one cover here, to one cover from the top, and show only one of them. Sorry, show only one of them. Okay, like that. And 08 is the secondary steel. 08, the steel must be secondary steel. Opposite direction. Yeah. The secondary steel. We put the secondary steel from here to here. So what is the distance here? Yeah, the distance 1 to 100, 800. So to get that value, we need to refer to the here. Sorry, I need to erase first. Where is the bar? Where is the simplified detailing? Yeah, we need to refer to the simplified detailing for the slab. Where is it? Yeah, all right. Yeah, okay. So you can see here, Ahmed. Join. Okay, you can see here. Look at here. Sorry, where is the cursor? 0.25 L. For the steel, the fixed end steel at the support, it must be 0.25 L from the face of the beam here. While for the reinforcement at the support, it is 0.3 L from here to the face of the beam support. Yeah? Look at here. Beam support. This is the face of the beam. Okay. Okay, 0.3 L, 0.2 L. Okay, back to our design. So here you can see here 800. Here is 0.2 L. 0.2 L. 0.2 L. Okay. While here is 0.3 L. 3 L. Okay. This is also 0.3 L. Okay. This is 0.3 L. Here 0.3 L. Just follow the guidance given. This is also 0.3 L. Okay. So other thing like here 0.1 L. If you don't cut, so we don't bother this one. If you don't cut the steel at the support. Okay.